Good morning, Dr. Pullen, Dr. Vickers, class. Today I will go over how a small metabolite, bicarbonate, directly binds to crocodilian hemoglobin and stabilizes the T state of the hemoglobin, lowering oxygen affinity and promoting tissue delivery. This comes from Dr. Takahashi in 2024, who used cryo-electron microscopy. That means we freeze hemoglobin particles and then collect thousands to even millions of images and average them to get a 3D electron density map. And then they fit the atomic model to this electron density map and look for the ligands that correspond. Here is the figure in question. And if we start with panel A, this panel shows the hemoglobin tetramer in the T state. You can see the 4 subunits colored separately. The most obvious visual feature here is the central cavity running through the middle. This open space is a characteristic of the T state conformation and is one helpful way to distinguish between the T and R states of hemoglobin. Our attention is then drawn to the boxed in region on the right side of this panel, which brings me to panel B of this figure. This panel is a top-down view into one of the pockets at the interface between subunits. The mesh you can see is the electron density from the cryo-EM, and overlaid on top of that is the atomic model. The remaining density that isn't explained by the protein is assigned to bicarbonate. The gray sections you see along the edges of this is a cross section of the experimental signal. If you kind of orient yourself on top of the image, you can see where the tryptophan is and get a good perspective. Moving on to panel C, we can see that this is the same basic principle, except it is rotated 180 degrees to look from the opposite side relative to the bicarbonate. This lets you see how the ligand sits in the pocket from the other angle. Now moving on to figure D and E, after using the cryo-EM to see exactly where that bicarbonate sits, we can then remove the electron density map and we are left with the bond line structures. And now we can see and measure the distances between certain ligands, residues, and functional groups relative to this bicarbonate. And this can help us explain why it's stabilizing, such as hydrogen bonding. And if we move on to figure E, this is the same as figure C, except minus the electron density map, where the only thing left is the bond line. And this can help us visualize, same as figure D, the interactions between neighboring residues and functional groups. Why this matters for crocodiles is during a dive, tissue metabolism releases CO2, which then becomes bicarbonate in red blood cells. That bicarbonate occupies these pockets we've discussed, keeping hemoglobin in a low affinity T state so it releases more O2 more rapidly to working tissues while conserving O2 for vital organs. One of the many reasons crocodiles can stay submerged for as long of periods of time